Generous introduction. See, I'll just start sharing the screen. Give me a minute. Yeah. Yes. So now the screen should be visible, right? So to all the participants, screen is visible.
Yes, sir.
Yes, sir,
Okay.
it's visible.
And I hope audio is also clear, right? I mean, we may face some difficulty with respect to audio in between, in which case, do let me know. Okay, good. So, yeah, thanks, Pauline, for such a generous introduction. But anyway, let's come to topic at hand. What I thought we will do for this session is to introduce Euclid's algorithm and to talk about some of its consequences. I mean, it is one of those algorithms or those simple ideas in mathematics which have a lot of avatars and which has actually led to a lot of progress in the subject, and it keeps recurring in different forms in the subject even as you go ahead and so on. So this is what I want to talk about, Euclid's algorithm and its consequences, right? uh, uh, and its consequences. Now, I thought this talk is meant for, I'm assuming people are, centrally interested in IOQM, which means that there should be some command in problem solving, which is what I thought I will focus on. But before that, I'll just have a bit of theory, okay, a very small bit of theory, so that we get, we firmly place ourselves with respect to notations and the ideas we are talking about. Okay, so to talk about, so what is Euclid's algorithm, right? Euclid's algorithm is something which we actually, if you look at the school syllabus, effectively it is taught as an algorithm and something students do at around standard fifth, right? We ask for questions like what is the greatest common divisor of two integers and so on. And there is also an algorithm to compute the greatest common divisor, which is usually taught. So let me remind that algorithm. Suppose you are trying to, let's say you are trying to compute greatest common divisor of 5 and 20. Yeah, or yeah, it's something. So we know, so this is the notation for greatest common divisor. Greatest common divisor, right? This we know is 5. Why? Because 5 divides 5. This is the notation for divides, yeah, and 5 divides 20, and clearly anything greater than 5 cannot divide 5. I mean, anything with divide 5 should be less than equal to 5. So this is clear that this is equal, right? GCD 5, 20 is 5. But suppose we have more complicated situation. Let's say we wanted to have a GCD of 6 and 14. Okay, 6 does not divide 14 and 14 does not divide 6. How do we compute this GCD? And I'll just recall, I mean, different state boards may have slightly different notation, but the algorithm that is taught is you have 6 and 14. 14 is smaller than 6. You begin by dividing. Now you have got remainder 2. Okay, and you replace 14. So you replace one of the larger of the numbers by the remainder you have got, and the smaller of the numbers, which is 6 in this case, will appear here now. Okay, so let me draw it. And you have 6 here. Now 2 is indeed divisible by 6, and therefore you have no remainder, and therefore you say GCD is 2. GCD of 6, 14 is 2. And this you can actually manually check. 2 divides 6, 2 divides 14, but there is no greater divisor of 6 and 14. Okay, I'm just trying to recall something which people have seen as notation, I presume. This algorithm is usually covered at school level, right? This is school algorithm for GCD. right? And what is formally happening? Let's now, we are senior school students, and we want to ask ourselves, we can get rid of specific numbers and just introduce n and m as variables. So suppose you want to compute GCD of n and m. Okay, what is the algorithm? GCD, you can, without loss of generality, assume that n is less than m or less than equal to m, right? Then what you can do, so this is the first step. M can be written as quotient times n plus remainder. Okay, this is a fundamental step. This is, let me say, this is a fundamental step. And this is whenever you have something like this available. So there is one and more property. Let me say R is between 0 and m. Sorry, let me write. Yeah. R is between 0 and m. Okay. So this is a fundamental property. So you are, and then the step says that GCD of n and m is same as GCD of R and n. So what you have done is effectively you have taken the larger of the two numbers, looked at the remainder when you divide by the smaller of the two numbers, and you have replaced it by the larger number by the smaller number. And now you recurse. Now you perform the same thing again. The size of the numbers have come down. I mean, n was less than equal to m, and R is strictly less than n. So it follows that minimum of R and n is strictly less than just a minute. Yeah, minimum of R and n, which is R, is strictly less than minimum of NMM, which is n. Okay, we had assumed n is less than equal to m, so this minimum is n, and R. Sorry, this should be n, right? So you're dividing by n. Okay, so the remainder has to be less than n. So minimum of R comma n is strictly less than R. Strictly less than n. So this minimum is R. Okay, good. So this
Uh,
algorithm you can yeah.
Sorry to interrupt you, but sir, what is the meaning of minimum?
The smaller of the two values.
Oh, okay, sir.
Okay. See, so this is what we were doing, right? We have written when we were trying to compute GCD of 6 and 14, we have written a smaller of two values here. Okay, and that carries over to the next step, but the remainder also comes into picture. So minimum of these two values is 2, and minimum of these two values is 6. So in each step, you are reducing a certain quantity, which is minimum of the two values. Okay. So therefore, this algorithm does not run indefinitely. At some stage, R must become 0. Okay. It cannot keep going down and down. The number you are dividing by keeps becoming smaller and smaller. And therefore, at some stage, there should be no remainder, so that the next stage of division is not at all possible. Okay. You cannot divide by 0 after all. And once R becomes 0, when R equal to 0, this is the termination step, then that is M equal to Qn, then GCD of M comma n is n. After all, n divides n and n divides m as well. Okay, so this is what the algorithm does, right? Are there any questions so far? I believe everyone has seen this algorithm in some form. All I have done is changed it into symbols. Yeah. Okay, good. Well, this algorithm has lot of theoretical consequences and is something which is indeed available in more than the situations we just encountered. So first of all, so this is available apart from integers as well. So in situations apart from integers as well, right? So example. So everyone, I hope, is familiar with polynomials. Polynomials in one variable. So let's say real polynomials. So the coefficients are real numbers, and you have polynomials in one variable. So we call it x. Okay. In this situation also, you can do the same thing. You can ask, given two polynomials, let's say x minus 1 into x minus 2 square, let's say fx equal to this, right? You can expand out this polynomial and gx equal to x minus 1 into x minus 3. You can ask what is the largest common factor. Well, there is no measure of size, but you can nevertheless ask, is there a common factor which every other common factor divides? And it turns out that there exists. So is there a common factor of fg which all other, so common factor, let me call h of f and g, which all other common factors h prime divide. That is, h prime divides h if h prime divides f and h prime divides g. Okay, it turns out there is one such common factor. Okay, and in this case, that common factor is clearly x minus 1. If there is a common factor of f and g, it is either a constant, which is 1, or it is x minus 1, right? So, but the way I have written polynomial, it was easy to read down such common factors. What if I expand this out? So what I'll get is x minus 1 into x square minus 4x plus 4. And this is x cube minus 4x square minus x square. So minus 5x square minus 4x plus 4x. So 0. And then minus 4. So this is this polynomial. Right? So this is this polynomial. There is some mistakes up here, right? X cube minus x square minus 4x square minus 5x square x appears with the quotient plus 4x because of this plus 8x, sorry. Yeah, that is the point. Plus 8x minus 4. Okay, so this is one polynomial, and the other polynomial is gx is x square minus 4x plus 3. Now, if I give you polynomials in this form, it will be very hard to write down what the common solution is, right? I mean, either you factorize it, which is by itself a hard problem, or you ask for, how do you ask for common polynomial? How do you compute the GCD directly without factorizing it? And then again, Euclid's algorithm comes into picture. What you do is you write down the larger of the polynomial. In this case, the larger be coming from degree. Okay, so you write down larger of the polynomial as the smaller of the polynomials times some quotient times some remainder. Okay, and this time remainder and quotient with will both be polynomials instead of being numbers. So if you try to do this, for example, in this case, what you will see is so what you can see is x squared minus 4x plus 3 into let's see, if I multiply it by x, I of course this is equal to x cube minus 4x squared plus 3x, and what I want is this to eventually become this polynomial, right? Eventually it should add up to this. So I subtract fx minus x square minus 4x plus 3 times x. I'm trying to estimate q. So I kill the highest degree first. Okay. So when I kill the highest degree, what do I get? I have removed x cube, so this becomes 0. Minus 5x square and plus 4x square, so this becomes minus x square plus minus x square. X, so you have plus 8x, and then you are subtracting 3x, so you get plus 5x. So I hope I'll not make a calculation mistake. Otherwise, we have to revisit at some stage. And then the constant. So we have -4, right? So we have this polynomial. Then I want to kill still, I want something, remainder has to be something of degree strictly less than. So I kill another copy of x square by just, so what I do is I look at -x square minus 4x plus 3 into x plus 1. So I subtract another copy of x square minus 4x, sorry, into x minus 1. I is that correct? Yeah. So I subtract another copy of x square minus 4x plus 3 from the whole business. Wait, there is some problem. This is fine. And then what I do is I look at this x square minus 4x plus 3 equal to, so when I add, what I'll get is x minus 1. Okay. This is what I get. Yeah. And this basically tells us that fx minus x square minus 4x plus 3 into x minus 1. So this equal to plus x minus 1. So I can take this as quotient and this as remainder. Okay. And I can now entirely replace the larger of these two. Sorry. As this as quotient. Sorry, what am I saying? This is this as quotient, and this is remainder. And I can replace the larger of these two, which is fx, by the remainder x minus 1. So what we get is f comma g, fx comma gx is same as x square minus 4. So, I'm not writing GCD before the brackets. This is a convention. A comma b means GCD of a comma b. Okay, this is a convention I'm following. So this comma x minus 1, and then it is now easy to see that if I put x equal to 1 here, it becomes 0. So x minus 1 divides this. So because the second term divides the first term, the GCD is just x minus 1. Okay, so I just demonstrated that even in polynomials, you can have a notion of GCD. And Euclid's algorithm, because it depends on lowering the remainder, can indeed be applied to compute that GCD. Not only do you have the GCD, but you can also compute the GCD effectively. Okay, so just give me some more time, 5-10 minutes, to write down the theoretical consequences of this, and then we'll start dealing with some problems. If you are lost, you can now come back. We'll now be talking about integers and so on. Hopefully, if we have time in the end and enthusiasm in the end, we'll come back to polynomials. Okay, so so we talked about GCD of polynomials now. But what are the consequences? Let's look at some consequences of Euclid's algorithm. Okay, so firstly, remember GCD of n comma m. So you write m as so let's go in the reverse direction. Okay, you have m equal to n. So I'm assuming n is less than equal to m. So nq plus r, and let me call it r naught. So r naught equal to, so now you will replace, so this is nothing but r naught comma n. Okay, and then you have n equal to r naught q1 plus r2, and now you replace n by r2, and therefore this becomes r2 comma r naught, right? Why am I calling it r2? I have to call it r1. Yeah. So, and then I do the same business again. I divide by r, so r naught equal to r1 q2 plus r2. Okay, and this becomes r2 comma r1. So this is a cascading equality which is coming in, and so on and so forth, right? And eventually you will have no remainder. So rk equal to, so some rk will become, when you divide by rk plus 1, it will just have a quotient and no remainder. Okay. So eventually it will start looking like this. It is forced to look like this because the size is decreasing. So this cannot continue indefinitely, but this is the only stopping step. So it looks like this. Now, if I reverse, what does it mean? See, in this case, GCD is RK plus 1, right? GCD is when you divide, so GCD becomes RK plus 1. Okay. Now look at the previous inequality, which is RK minus 1 equal to RK QK plus 1 plus RK plus 1. Okay. Which means that RK plus 1 can be written as a linear combination of RK and RK minus 1. So RK plus 1 equal to QK plus 1 RK minus RK minus 1. Okay. Now I can do the same business for RK minus 1 to get RK minus 1. Sorry, RK. I can do the same business for RK first. So RK equal to QK RK minus 1 minus RK minus 2. So this is 1 and this is 2. Substitute 2 in 1 to get RK plus 1 equal to QK plus 1, and RK becomes QK RK minus 1 minus RK minus 2 minus RK minus 1. So if you expand this out, so RK minus 1 comes with some coefficient, QK plus 1 times QK minus 1. And RK minus 2 comes with some coefficient, QK plus 1 times minus 1. So this becomes M1, let's say, times RK minus 1 plus M2 times RK minus 2. Is that fine? Yeah. RK plus 1, which is the GCD, becomes a linear combination of RK minus 1 and RK minus 2. Again, if you take the equation for RK minus 1 and substitute, so this will start looking like QK minus 1, RK minus 2, minus RK minus 3, plus M2 RK minus 2. Okay. And this will, defining M2 and M3 appropriately, this becomes M2 times M2 times RK minus 2 plus M3 times RK minus 3. See, I defined M2 to be sum of this product and plus this, and M3 to be minus of M1 QK minus 1. Okay, so what is the point? You can keep continuing this, and eventually what you will get, that it is some many number, I do not know how much, times M. So okay, I'll call these constants M and N. AM plus BN. Okay, where A and B are integers in this case, because we are talking about factorization in integers, or if we are talking about factorization in polynomials, these are polynomials. And this is a very useful thing. It says that GCD is actually a linear combination of the numbers you are computing GCD of. Okay. In fact, it is the smallest possible, I mean, up to sign, the smallest possible linear combination you can get, because GCD will certainly divide M, GCD will certainly divide N. So GCD will also divide AM plus BN, right? GCD will also divide the sum here. And therefore, GCD will divide any such sum. And therefore, it's the smallest possible. So let me rephrase this. Let me just write it and it should be clearer. GCD equal to smallest possible value of AM plus BN, and let's put modulus up to sign. A and B are, so let's talk about only integers. So A and B are integers. So this sign is used for integers. So this is a very, very useful result. It tells you that GCD is computable using summation, not merely by trying to factorize. If you compute all possible linear combinations, then the smallest number you will get is actually GCD. This is a relation between addition and the way we traditionally define GCD, which is using product. Okay. Anyway, consequence. So this formula has a consequence. So, we all know these facts. let's say if a prime divides product of two integers, then prime divides A or prime divides B. Remember where P is a number, P has no factors apart from 1 and P. Okay. See, think about it theoretically, what is happening. You defined a prime number using what are its factors. Okay. You did not define how a prime number defines another divides another number, but what are its factors? And using that, you are able to conclude that if it divides a product, then it should divide one of the numbers. So a problem about, an assumption about divisors becomes has a consequence about what it divides. Okay, this is the way you prove that every number has a unique factorization. How it's an immediate consequence of what I have done so far, but just to give you some exercise, I leave this as an exercise. Okay. Now, can we try to make so Pauline, I do not know, this is an online class. Can we try to make the class interactive in the sense that I can start giving some problems which have, a use of Euclid's algorithm in place? Let's see the class response. That will help me gauge where we are, and then we can cover some further theory if needed. Will that be possible? Hello.
Hello, students. Yes, sir. You can continue, I think, with problems.
Okay, that's good. So let's begin with the IMO problem. But it is the easiest IMO problem which ever came. This, I think, appears in 1959 or something like that. So which is more than 70 years now. No, more than 60 years now. And okay. For what n? What is the for what n? Okay, so rather show that fraction 21n plus 4 and 41n plus 3 is in reduced form, right? Reduced form means that numerator and denominator, nothing can be cancelled off. 4 by 6 is not in reduced form. Okay. So does anyone want to suggest how should we proceed?
Like GCD of 21n plus 4 and 41n plus 3 should be 1. Then we can say that.
Good.
Yeah.
Right. So GCD. So let me write it. Proof. There should not be a common factor. In particular, there should not be a largest common factor. Conversely, if the largest common factor is 1, then there is no other common factor other than 1, because any other common factor will divide 1. So you cannot cancel off anything if GCD of 21n plus 4 and 41n plus 3 is 1. How do you compute this GCD? Okay.
Like, sir, there is a, yeah, sir, there is a property like GCD of A comma B, then
Good.
it's equals to GCD of A comma A minus B.
Okay. So GCD of A comma B is actually GCD of A comma B minus anything times A.
Yeah,
okay?
yeah, sir.
And this already can be seen through this linear summation property. After all, you are varying all AB over Z, and you can easily see that these two have same GCD. You can also give a division argument, which is not very hard. But this property, let's assume. So what is? So let's just subtract. So this becomes okay. So LHS becomes GCD of 21n plus 4, and I'll just subtract this. So this becomes 20n plus 3. Okay. Now I subtract the second thing from first. I can repeat the same thing. I mean, GCD of A comma B is the same as GCD of B comma A. So this becomes n plus, sorry, I have made a mistake. I have to subtract 4 also, right? So 21n minus 1. Please correct me when I make a mistake, because I'm very prone to making these mistakes. Yeah. So you have 20n minus 1, right? You subtract 3 minus 4 also. Now you subtract again this side, so you get n and you are subtracting -1, so that becomes +1. So n plus 5, 20n minus 1. Everyone is clear what I'm doing? Yeah.
Yes,
Just
sir.
ask me. This, this is, yeah, quite easy. And then you subtract 20 times this much. Q can be anything, so I take Q to be 20. Here Q can be anything, so I take Q to be 20. So when I subtract 20 times this, what do I get? 20 and completely cancels off. 20 into 5 is 100, so I get minus 101. Okay, and so therefore this becomes GCD of n plus 5, comma 101. Is that correct? Did I make a mistake anywhere? I hope not. So when I subtract this, I get 20n minus 1. When I look at 20n minus 1, and this is, when I subtract this, I get n plus 5. And when I subtract this, 20 times this, I get 101. So what is this? What are the possibilities for this? Anyone? What can GCD of 101 comma n plus 5 be? It can be either 1 or 101, because this number is prime. It has to be a factor. Okay. Am I audible?
Yes, sir, you're audible. Students, you are asked something.
Is this fine? I mean, just say yes or no. I mean, it will allow me to stay in. Yeah, I mean, I'll have some sense of what is happening. Have I made a mistake in calculation somewhere? I was expecting, can someone, I hope I've not made a mistake. 21n plus 4, 41n plus 3. I subtract this. 41 minus 21 is 20. 3 minus 4 is minus 1. And I get n plus 5 and 20n minus 1. And then I look at, yeah, so this seems fine. Yeah. Students, is this fine? Or if someone finds a mistake, please let me know. So this is either 1 or 101. Of course, if it's 1, we are done. So the only way it is that it has to be 101. Right? Everyone can unmute themselves if possible. I mean, I don't know if that is possible. That will allow me to get a sense of the class. I don't know. Okay. Problem solving, it's better to be interactive. Otherwise, we are very quickly lost.
Respond to Professor Vaish. If you have any questions or if you think that it's all right, then say yes or no. Badibrat.
Yes, sir.
So you respond, please.
Yeah. See, if you will speak something, it will just make me have some sense of the class. I mean, otherwise one gets quickly lost. Okay, let's anyway continue. So what we see here is that it is either 1 or 101, because this is prime. Okay, if it is 1, we are done. So that is the case that it is 101, and it is indeed possible to be 101. If n equal to 96, then GCD is 101. Okay, so maybe I framed the problem wrong. So maybe I'll add here for n less than 96. I think the original problem was to find the smallest n where it is not in reduced form. So the original problem is framed wrong here, but we actually managed to solve it completely, because all we said is we managed to compute its GCD. It is going to be 101 or 1, and 101 is possible only when n is congruent to -5. N plus 5 is divisible by 101. So the smallest such number is going to be n equal to 96. Okay, n is assumed to be positive here. Okay, so this was just a starter. This is a very easy problem. Let's take 5 minutes to compute the following problem. What is the largest value of GCD 100 plus A square, comma 100 plus B square if A and B are consecutive integers? So, there is a sequence. I can look at 100 plus 1 square, which is 101. And then I look at 100 plus 2 square, which is 105. And then next number will be 104, 2 square, 104. And then you have 109, and then you have 116, and then you have 125, and so on. Right? This is a sequence. And I look at the GCD of consecutive integers in this sequence. And the question is, what are the possible values? What is the largest possible value in particular? Okay. If you have pen and paper, take 5 minutes to compute, and then maybe we can discuss. And if you have any ideas, you can also speak out loud. Okay. So remember what we are trying to do. We are trying to compute this GCD, right? Which you want it to be the largest possible. And A and B, you want to be consecutive terms in the sequence. So what can you say about if I assume A is n, then B has to be n plus 1, right? I mean, I can assume B is greater than A, the further one. Is this fine? Yeah. And then what I can do is I can ask if I can compute GCD of 100 plus n square and 100 plus n plus 1 square. Okay. And this is an easy computation. There is nothing really. 100 plus n square plus 2n plus 1. So I'll write it as 101. And remember, I said division and quotient. That's how you compute the GCD. So you try to divide this by this. Well, you think of it as a polynomial in 100 first, and then we'll see what happens. So this, the remainder is when you subtract 100 plus n square. So you get 1 plus 2n. Okay. So you get 1 plus 2n. And then what you can do is this GCD. So remember, both n and n plus 1 cannot be simultaneously even. Okay. So both 100 plus a square and 100 plus b square cannot be simultaneously divisible by 2. Right? If this is even, then this is odd. And conversely, so I can freely multiply by 2. 2 is not a problem. So so this GCD is also same as GCD between 400 plus 4n square and 1 plus 2n up to a factor of 2. Okay. I can eventually drop all powers of 2, and multiplying by 2 would not change the GCD up to a factor of 2. Sorry, 1 plus, 2n square is good enough. Let me just multiply by 2. This equality is up to a factor of 2. And then what you have is, you can multiply this by n and subtract. So what you will get is 200 minus n and 1 plus 2n. So I'm multiplying this by n and subtracting from the previous thing. Okay. And then I can multiply this with 2 and add. So I get 200 minus n, 401. And as before, what we have got, see, this is what we are doing, quotient remainder. Each time the degree is being reduced, and eventually what you will get is something of degree 0. Okay. And this degree 0 thing, I mean, because we are in integers, we cannot immediately say if 401 divides 200 minus n or not. That depends on specific n. But it is clear that the largest GCD possible can be just 401. Okay, and that happens when 401 divides 200 minus n, which is same as saying it divides n minus 200. So e.g. for n equal to 601. Okay, so it's much further down. If you try to manually compute, it will take you will not be able to. But it's clear that this can be the GCD, provided n equal you go far enough. But nothing larger can come as a GCD, because this thing is constant now, right? I mean, you cannot push a GCD, you cannot compute a divisor which is higher than 401 for this. Yeah. So I hope this problem is clear. Are there any questions? See, this is the drawback of online teaching. We completely get lost as instructors if the class is with us or not with us. But
Sir, why you?
Yeah. Tell me.
Why, sir? Why you multiply with 2? Like,
no, we can multiply with 2. It's not necessary to multiply with 2. But the reason I multiplied with 2 is because I wanted to have some multiple of this. Okay. When I subtract from this, I should be able to kill the highest degree term. Now, if I don't multiply by 2, I have to multiply it by half, which takes it away from integer. So GCD does not make sense. Okay. So what I say is that this GCD is same as this GCD, but up to a factor of 2. So I can multiply. So what I'm saying is, so let me write it down here. GCD of AB equal to GCD of 2AB if 2 does not divide. Okay. So or GCD of AB equal to, twice GCD of AB equal to GCD of 2A to B. See this. So what is GCD? It is the highest common factor, right? So when you compute GCD of 2A comma B, either this 2 is no longer, I mean, it does not change the GCD at all, or has introduced one extra 2 in the factor. Okay, that's all there is. It can do. So this is what I'm using. So when I say up to a factor of 2, this is what I mean. And I do it because, yeah, I do it so that in the next step, I can actually, I can go on with this computation. Okay, good. So this is another problem. Let's do a kind of problem which can appear in IOQM. Okay, so so let's do another problem. Yeah. Okay, so find n least, of course, positive integer. In fact, let's say n is even, I want it to be greater than equal to 1000. Okay, such that GCD of 63 comma n plus 120 equal to 21, and GCD of n plus 63 comma 120 equal to 60. Okay, so yeah, I mean, this is something that can appear in IOQM, except that they would not ask for n, but because they are constrained by how their multiple choices have to look, they will ask for sum of digits of n or something like that. So maybe find sum of digits of n. Sum of digits of n, where n is least positive integer, which is
generic problem. Sir, you can take generic one, no issue.
Yeah,
you can take generic problem, because IOQM, they will I mean they will set according to their options from 00 to 19.
Yeah. So we can just try to compute such a n, and whatever they ask, product of digits or sum of digits, that you can do accordingly as they have asked. Okay, so what is a good way to approach this? So let's see solution. We want n to be greater than equal to 1000. So let's work with n greater than equal to 1000. So what we'll get is n equal to 1000 plus k, where k is greater than equal to 0. This, often simplifies life, but may not sometimes, but nevertheless. And what we have is, this is 1000 plus 120 plus k, right? 21 equal to this. This is equal to 63, 1120 plus k. Okay. 1120 plus k. Now let's, we can subtract some multiple of 63 from this side. That is something we are certainly allowed. We already saw that. So let's do that. See, if I try to divide 6, see, let's, I'll just simplify. What is the remainder when I divide by 1120? So 63. So we have to divide 1120 by 63. So 63 into 17. I'm cheating a bit. I'm using calculations on a computer to speed this up. Minus 17 into 63 plus k. Okay, this GCD is also going to be this number, and this is 1120 minus 1071. Okay, plus k. And when I subtract it, what do I get? So 20 here and 30 here, 50, so 49. Okay, so I get 49. Let us look at this. So we know that this is 21, right? Which means that 21 must divide this and 21 must divide this, right? So let's see. 21 divides 63, that is fine anyway. And 21 divides 49 plus k, which means that k is congruent to minus 49 mod 21. I hope everyone is familiar with this notation. If you are not, please interrupt me and ask. Usually, it's better to do Olympiad problems in a very interactive mode, but that's okay. So now, so 63 minus 49 will be what? 63 minus 49 will be 14. Okay. So this is 14 mod 21. So this is one relation I got. K is congruent to 14 mod 21. This is 1. I use the other thing. Okay. So this is from this. So remember, there are two constraints. This is one constraint, and this is the second constraint. Okay. The first constraint, so I have assumed this once and for all. And the first constraint then translated into this. Okay. And that has consequence that k is congruent to 14 mod 21. Okay. Now I have to work with the second constraint. So the second constraint was n plus 63, 120 is 60. Right? Is that correct? Yeah. And this, remember, n is 1000 plus k. So this becomes 1063 plus k, 120. Right? The GCD is this. And then I can get rid of 12, 8. So 120 times 8 is 90. Sorry, 96. Yeah, that should be good enough. So minus 120 times 8 plus k, 120, and this is 1063 minus 960 plus k, 120, and this becomes 103 plus k, 120. Okay, so what we conclude is that k is congruent to, see, and this we know is divisible by this, we know is 60, right? So what we conclude is 60 divides 103 plus k, and this implies that 60, so k is congruent to minus, so k is congruent to minus 43 mod 60. Okay, I mean, okay, I can say maybe minus 103 to begin with, which is minus 43, which is also same as 17 mod 60. Okay, so this is another information I get. If I break it down into primes, what does, so there are two informations, right? This is 1 and this is 2. This I can simultaneously try to solve. So k congruent to 14 mod 21 and k congruent to 17 mod 60. What is the smallest possible solution? K is congruent to 17 mod 60. Well, you can actually reduce it because it is congruent to 14 mod 21. You know that k equal to 7 times k prime. Okay, so what you will get is k prime is congruent to 2 mod 3 and k prime is congruent to just a minute, 31 mod 60. Anyway, eventually if you do the problem, yeah, is this clear? Okay, let me not skip the steps and just do it. So k equal to 7k prime, right? This implies that, see, why I'm saying k equal to 7k prime? Because k is congruent to 14 mod 21. So k minus 14 is divisible by 21, in particular by 7, and 14 divisible by 7 implies k is divisible by 7. So I can take k equal to 7k prime. And this implies that 7k prime is congruent to 14 mod 21, which is same as saying k prime is congruent to 2 mod 3 actually. Okay, once, because 7 is congruent to 1 mod 3 and modulo 7, this is anyway satisfied. K congruent to 17 mod 60 similarly reduces to so this 16 mod 60 similarly reduces to k is congruent to 0 sorry, k is congruent to 2 mod 3, sorry, k prime is congruent to 2 mod 3. So this is 7k prime, and 60 has 3 factors, 3, 5, and 4. That's what I'm doing. K prime is congruent to 2 mod 5, and k prime is congruent to 1 mod 4. Okay. Now it's not very hard to solve this problem. Okay. Easy to find such a k prime now. If I remember correctly, this turns out to be 9. Yeah, I don't remember what the answer is, but this you can now try solving. Are there any questions? Does anyone has an issue? I mean, now we have reduced to finding a k prime which has these remainders, and this can be easily done. Does anyone want me to go over how to solve this?
Like, sir, I have a better like a way to
You have a
like
better way? Sure.
yeah,
Sure.
yeah, like yeah, sir, like if we take mod 21 in the first equation, that is 63 comma n plus 20, 120 is equals to 21, then n congruence 6 mod 21 that's that come out from the first equation.
Yeah.
And congruence 57 from the second equation.
63, n plus 63. So n is congruent to minus 3 mod 60, and n is congruent to
then we can
like directly do it.
Yeah, we can write that n is equals to 21 a plus 6, where a is any number. Like then we can compute like n is equals to 60 b plus 57 from the second equation.
Sure.
Yeah.
So,
then,
but still you have to solve congruence relation. I'm trying to solve congruence relation for k for n equal to 1000 plus k. You can try to solve congruence relations for n and then ask which congruence class is n greater than equal to 1000.
Yeah, like then the answer came out 1917, and some of the digits are 18. Answer. Yeah.
Exactly.
Yeah, sir.
Exactly. That's correct. So some of the digits I remember is 18. So I believe the answer is correct. So it will turn out to be 1917. But but all I was saying was that what you can do Yeah. So anyway, that's a correct solution also. And this here, what we have done is we have gotten rid of the fact that I have put n equal to 1000 plus k. That's the only simplification. Otherwise, I'm doing the same thing in the expanded form. That's all. Okay. There is
Okay,
is
sir.
this fine?
Okay, sir. Yes, yes.
The same solution, except that I'm using n equal to 1000 plus k, so that I can get rid of the constraint that n has to be greater than equal to 1000. But you are right. After finding the remainder, you can reduce the constraint later. Okay. Okay. Let's do something more challenging. This is these were easy. We have about half an hour. Let me ask you this question. So exercise. Suppose I look at 1 plus root 2 to the power n and call it an plus bn root 2. Remember, when you expand it out, sometimes, when you use the binomial coefficient, root 2 will appear with even powers or odd powers. And when root 2 appears with even powers, it just becomes integers. You sum them up. When root 2 appears with odd powers, up to 1 root 2, it is again an integer. So you sum all those integers up and call that bn. And when it appears with even power, the summation is an, right? So it always can be written uniquely in this form. Okay. Then claim an comma bn is 1. Okay. It's not very hard, but anyone wants to propose how to do it? So what, when you are given something happens for all n, you want to prove something happens for all n, where n is an integer. What is the first thing that comes to mind? So you should think of induction. Okay. So let's do the proof. So this also not very hard. Once you get the idea that induction is something you should try. So proof n equal to 1. So I'm trying induction. So I have to do base case and induction step. So base case is an equal to 1, bn equal to 1, and therefore GCD of a and bn is 1, 1, which is 1. Right? If n is 1, then 1 plus root 2 to the power 1 is just 1 plus root 2, and therefore you have these things. Okay. What happens at the induction step? Suppose n equal to k, ak comma bk is indeed 1. Okay. What happens when you look at n equal to k plus 1? So this assumption, and from this I'm trying to reduce that n equal to k plus 1, also the same relation happens. So let's look at it. So remember, we are trying to look at ak plus 1 plus bk plus 1 root 2. This is same as k plus 1, and this becomes 1 plus root 2 to the power k times 1 plus root 2. Okay. Now, once you look at this by induction hypothesis is ak plus bk root 2, and this is 1 plus root 2. Okay. And then I do the same multiplications. Now I can just multiply. So ak plus 2bk plus ak root 2 plus bk root 2. So ak plus bk, right, times root 2. I hope I have not made a mistake. ak bk root 2 and bk root 2 and ak root 2, that's fine, and ak plus 2b. Yeah, this is what we get, right? So from this you conclude ak plus 1 equal to ak plus 2bk and bk plus 1 equal to ak plus bk, right? And therefore, what is GCD of ak plus 1 and bk plus 1? This is ak plus 2bk, sorry, ak plus 2bk, comma ak plus bk. Now I'm allowed to subtract. So I subtract the second term for the first term. So I get bk comma ak plus bk. And then I subtract the first term from the second term. So I get bk comma ak, which by induction hypothesis is just 1. Okay. So once you get the idea, it is induction. Euclid's algorithm allowing you to play with the GCD sign quickly leads to the solution. Okay. So you should always, so if you feel stuck in Olympiad problem, the first thing to do is to try to think, what are the approaches I know and which one should I try? And you try one and push it as far as you can. If you get stuck, you try another. Induction is one approach, computation of invariants is another approach, do some small calculations and things like that. But anyway, this is a simple problem. Let's stop here. Let's now give one challenging problem. Okay. So this, I believe, is not so simple. So the idea is this. Let's say A1 is 200, 2000, you can pick any two consecutive numbers. We can give a solution. So let's take A1 equal to 2020 by 2021, let's say. Okay. And then what you can do is AK, suppose AK is M by N in reduced form. Okay. Define AK plus 1 equal to M plus 18 by N plus 19. This may not be in reduced form. Okay. Just because M by N was in reduced form does not mean M plus 18 by N plus 19 is going to be reduced form. Some cancellations may happen. So after cancellations, the next step again defines you add 18 and you add 19. Okay. Then the question is, what is the next time AK equal to T by T plus 1. So maybe I should write like this, T by T plus 1 for some integer T. Okay. So yeah, everyone understands the question. I mean, see, these two numbers are not consecutive, right? You have increased the numerator by one less than what you have increased the denominator by. So anyway, if no cancellations were happening either, even then these numbers won't be consecutive. Okay. But suppose, see, what we want is, when does it happen that it is AK equal to T by T plus 1? It is already T by T plus 1 to begin with.
I just want to interrupt, sir. Dear students, do you have questions? Why the sir has defined that say n plus 1 is equal to n plus 18 by n plus 19? If you have questions, freely ask, I think.
Yeah.
Okay, sir, continue.
Okay. Okay. So are there any suggestions what to do in this case? See, this is part of the problem.
Just I was asking students.
We can, sure. Yeah. No, I was asking other students. So are there, see, what do you want? We have A1 is in this form. There is no, we can.
Sir, we can transverse it in its form so that the value comes out.
Okay. How do we transform this equation? Yeah. Any suggestion? See, AK
Sir,
is M plus 18 by N plus 19. And this is the question, when does it become T by T plus 1? Shilpa. You're saying something, Shilpa? You are muted now.
Shilpa, you can.
I hope you're not.
Shilpa, your question is not
muted
clear.
Now.
Okay.
Sir,
It was a suggestion.
my network is not working properly, I think.
Okay. So how do you propose we transform this problem? Okay. Yeah, the network probably is not clear for Shilpa. So let's carry on. So see what we have is A1. So let's do the first few steps of computation, right? Let's try to see what happens. So you have what did it define? 2020 by 2021. We could have begun 2021 by 2022. That's also fine. Huh? So what is next A2? They don't have a common factor, clearly. So they are consecutive, so they don't have a common factor. So you add 18 to both. So what do you get? 2038 by 2000 and sorry, 18 and 19 to the denominator. So 2040. Yeah, is that correct? N equal to, so I added 18 on the top, so I get 38, and 19 to the bottom, so I get 40, right? So already I require some cancellation to happen. So I get to 1020, so sorry, 1019, and then I have 1020. So good, we already found a solution. We tried the first step. We found that we can reduce it in a form such that it becomes t by t plus 1. Okay, so let's modify the problem. My memory might be, so this case is easy. Okay, easy. So let's work with the second case. Let's say A1 equal to 2021 by 2022. Okay, in this case, when does it become t by t plus 1? Let's try to work this out. So this is done, right? So let's take the second case. A1 is 2021 by 2022. So then what happens? A2 becomes 2000. You should always try out some low cases just to get an idea of what is happening. 39. Yeah, that's correct. I have to add 18, and then I have to add 19 to the bottom, which will add 2041. Okay. Now these two things differ by 2, and they don't have a common factor. I mean, they, the only common factor can be 2, but they both are odd, so they can't have a common factor. So okay, the next step is also clear. I have to make no cancellations. Sorry, I have to make no cancellations, and I add 18 again. So I get 2000. So 57, right? And this I get. So now I have to add 90 to this one. So when I add 19, I get 2051, 2060. Okay. Now these two things differ by 3. See, this difference was 1, numerator and denominator. This difference was 2. This difference was 3. And Euclid's algorithm tells me, therefore, that any common factor must be a factor of 3. And we can easily see that 3 does not divide either of these terms. So this is something which is happening, right? This gives us a suggestion that the common factors keep increasing. Okay. Unless, so at each step, the common factor increases, and then it divides one of them. I mean, both of them, and then it comes down and something like that. So let's ask this question. So question: is smallest k such that AK was not in reduced form? This is what I'm asking. Okay. See, A1 was in reduced form. So maybe a change of notation will help us. AK plus 1. Okay. Smallest k such that AK plus 1 was not in reduced form. Okay. So for k equal to 0, that is A1, this is in reduced form. Just, yeah. So this is in reduced form. Then I did the next computation. This was also in reduced form. Once I know something is in reduced form, I can easily tell what the next number is. Otherwise, I have to cancel. But otherwise, if it is in reduced form, it's clear. You have to add 18 to the numerator, 19 to the denominator. Okay. So how do I compute? Well, this is quite easy. So AK plus 1, AK plus 1 is not in reduced form, but before that everything was in reduced form. So you were just adding 18 to the numerator and you were just adding 19 to the denominator. So this will be, you have 2021 plus 18K and 2022 plus 19K. Okay, so this is what it will become, right? You have added 18K many times. So, you go from A1 to A2, you have added 18 ones to the numerator and 19 ones to the denominator. And I'm assuming that this is the smallest K such that AK plus 1 was not in reduced form. So I keep doing it. I don't have to make any cancellations is the assumption. And AK plus 1 has cancellations, which means that the GCD must become larger than 1. This is where GCD comes into picture. Maybe I'll use some color. So the question is, when does this happens for the first time that this becomes greater than 1? Okay, this is what we are asking. Now this is much simpler, right? We are asking when does this become greater than 1? So good. So what we do is this GCD we can compute. So this is 2021 plus 18K. I subtract this here. So I get 1 plus K. Okay, is that correct? Yeah, I get 1 plus K. Now I take 18 times this and subtract. So I get 2021 minus 18, which is 2003, I believe. Yeah, is that correct? Yeah. And K has cancelled off. So you get 1 plus K. So this GCD is same as GCD of 2003 times 1 plus K. Is 2003 a prime number? Anyone? Does 2003 have factors or is it a prime number?
So it's a
Okay.
prime number.
It's a prime number. Why? So I'm just trying to imitate what will you do in exam, right? So that 50 square is 2500. So if it has a factor, it has to be less than 50. It clearly is not divisible by 1, 3, 5. Is it divisible by 7? Let's leave it aside for a moment. Is it divisible by 11? No. I mean, these things have quick checks, right? So is it divisible by 17? You have to ask, right? Is it divisible by 19? And so on. So you just check if it is a prime number or not. The point is, look for the smallest factor of 2003. This is what the GCD should become. If at all, it has to, if it has to be greater than 1. The smallest factor, which is not 1, smallest factor greater than 1 of 2003. This is what the GCD would become. And then you would divide by this factor. Okay. So in that case, AK plus 1 will become, so let's say this is D, where D divides 2003, smallest factor. Okay. So then AK plus 1 will become 2000. So what will it become? Just a minute. We have to go up. So it is 2021 plus 18K by 2022 plus 19K. Yeah. So 2021 plus 18K plus 2022 plus 19K. And this is 2003. So remember, this is 2003 plus 18 into 1 plus K. Is that correct? Yeah. And this is 2003 plus 19 into 1 plus K. Okay. So the common factor, when you actually make the division, this becomes 2003 by whatever the common factor D is, 18 1 plus K by D by 2003 by D plus 19 1 plus K by D. Okay. So this is what happens now, right? So yeah, give me a minute. I have to also think what is happening. Yeah. See, is the screen sharing working fine? I'm having some
Yes, sir.
difficulties here, technical issues. Yeah, it says that your screen sharing is paused. I hope you all can see the document. That is not a problem, right?
Yes, sir.
Yes.
Okay. ठीक है. So that is fine. Let's try to come to this solution. Yeah, what do I do now? So if you say if D is indeed 2003, as you say, right? Then, oh, by the way, so this is the point. Yeah, sorry, I was making a mistake. Let's see. See, K is the smallest such integer such that 1 plus K divides to, see, we are asking for the first such step, right? So the first such step will happen when 1 plus K will be a factor of 2003 itself, right? Not merely the GCD will be D, but, okay, so let me write it here. First such D will appear, D greater than 1 will appear when 1 plus K equal to D. The smallest possible choice being the factor of 2003, but it appears when 1 plus K equal to D, right? You are increasing K 1 by 1, you encounter non-factors of 2003. At some stage, you encounter a factor of 2003, and that is exactly the stage when this GCD becomes greater than 1. So, okay. So, therefore, what you conclude is that, okay, so let me write it here. So, it is already written. So 1 plus K equal to D happens. This is the important part, that we already have 1 plus K equal to D, which means that this equality reduces to 2003 by D plus 18, because 1 plus K equal to D, since 1 plus K equal to D, and 2003 by D plus 19. Okay. D is probably 2003, probably some prime factor of 2003. I don't know. I have not computed whether it is prime or not. Okay. I am like, you have to do that calculation if you want, but you don't necessarily. For this proof, it's not necessary. So what has happened? This is T. This is T. And this is T plus 1. Right? They now differ by just exactly one integer. Okay. So therefore, the answer is you find the smallest factor of, smallest factor such that 1 plus K divides 2003, and that AK plus 1 will not be in reduced form. Not only will it not be in reduced form, it already becomes T by T plus 1. So if, as you say, 2003 is prime, so answer, if 2003 is prime, you take 1 plus K equal to 2003, that is K equal to 2002. Okay, so this is after 2002 steps, you get the required GCD. Okay, so that completes what we wanted. AK plus 1, which is
Problem,
A
sir.
2003, is of the form T by T plus 1. Yeah.
It was a nice problem. I liked it.
Yeah.
Very good.
Yeah. This is an interesting problem.
Can you
Okay,
propose?
so I'm done. I mean, it's 8:30, so I'll partly stop. Yeah, you're saying something. Sorry.
Problem with the year 2023, because in most of the Olympics we find every year that there is a questions involving the year, that particular year. That has
Yeah.
I have seen all the papers.
See, this problem has appeared somewhere. I mean, I was looking for problems around Euclid's algorithm when I encountered this. So yeah, it's not an original problem. Let me put it that way. Yeah.
That's nice problem you have chosen. I liked it.
Yeah. Thanks. Yeah. Okay, so it's already 8:30. I'll stop. If there are any questions, we can have a discussion or we can take it further, whatever way. Yeah.
Yes, dear students, if you have any questions, queries, you can ask.
Yeah, so why you choose that AK is not reduced form? Like,
That was the definition. That was the problem itself, right? The problem said that if you write AK in reduced form m by n, then the next thing is m plus 18 by n plus 19, right? If if you write m by n equal to 2m by n, but 2m plus 18 by 2n plus 19 is not equal to m plus 18 by n plus 19. So defining the next term requires choosing AK in the reduced form. Okay, without writing AK in the reduced form, you will not be able to, so without writing AK in the reduced form, you will not be able to correctly define AK plus 1. Okay, so that's the idea. So
okay,
if
okay,
you
thank you.
Shilpa. See, some names
Excuse me,
appear
sir.
popping out on the board, but yeah, you're saying something.
Sir, in that first form which you have written 1021, sir, you have written like that 2021 by 22. So you could, can we do it like that? We can reduce it by its lowest form. Then we could plus it with the m plus 18, then n plus 19.
Yeah,
So can
that is
we
what we
do
did, right?
that in other form also?
No, the definition says that you have to take the reduced form and then do it. If you do not take the reduced form and do it, then you will end up producing something which may not be equal to what the definition says. So if you have to work with this problem, which involves a particular definition, you are working with this sequence. Okay, it's just that by hand computation is what you need, but you may not get something which is not in reduced form very further down the picture.
And sir, can I ask you one more doubt?
Sure.
Sir, the formula which you have used here, that AK should be reduced in its lowest term, does it have any specific name for this formula, or any is it an identity or a principle?
See, we are not talking about theorems and interest. See, we are talking about problems which are interesting from the perspective of IOQM, which means that some of them are not so well motivated. All right, I mean, this is just a fun puzzle. I don't think I'm not aware of a good motivation of this problem, why we should, and therefore these names have not been defined. Okay, this sequence would not have an interesting name. I'm not familiar with one. Okay,
Okay.
that's, yeah.